Okay. Okay, so let's take the most simplest case. Okay, I think we have already discussed, but anyway, let's brush it up. So we are considering silicon crystal. Okay, perfectly bonded silicon crystal, no defects, nothing, something like this. Okay, all electrons are participating in that covalent bonding. Okay, no electron is available. So this is the scenario at 0 Kelvin, right? What does it tell you? It says that we'll have all the electrons in the valence band, right? Fine. Okay. Now, as you increase the temperature, what happens? Electron gains energy. It gains thermal energy, and maybe some of the bonds will be broken, and there will be some, electrons. Okay, something like that. So one of the bonds is broken. Okay, so this electron is now free. Okay, and so as it moves, we have empty uh, spots which we call hole. Okay, now this hole can be another electron can come here and sit. So that means we have electron hole pair generation. Okay, at finite temperature. Is it clear? So then how do we sketch it here? Something like this. So we had many electrons, but maybe as we increase the temperature, some of the electrons are jumping, okay, or excited from valence band to conduction band. Okay, so in conduction band we have density of states, allowed energy levels, and why it's been able to jump. The reason is that's a Fermi-Dirac stat. Okay, as you remember, as temperature increased, so it got skewed, right? That means there is a finite probability of finding electron higher than the Fermi energy level. Okay, so note that at room temperature, what is the thermal energy roughly? What is the thermal energy? 26 mega. So what is the band gap of electron? Sorry, silicon. So then, do you understand why should an electron jump from valence band to conduction band when the band gap is that large? Right? Valid question. Your band gap is much higher than the thermal energy, right? Then
Actually, the energy of some electrons will be high.
that's the answer. Okay. So it's the distribution. Okay. So in the Fermi-Dirac stat, if you remember, it is a distribution. Okay. And there are some electrons, very few in number. There are some electrons, okay, which will be excited and that can overcome this barrier. Good. Okay, so those electrons are we call intrinsic carrier concentration. Okay, so always we write electron and hole pairs in pairs because every time you generate electron you also generate a hole. Okay, that's why it's called electron hole pairs. So this number is typically 10 raised to 10 at room temperature for silicon per centimeter cube. Okay, I'm just giving you the number. Okay, we'll calculate it. It's okay in the next to next slide, but I'm just giving you number. But is this number large, small? Do you have any idea? If you take Avogadro's number or silicon density, that's of the order of 23, 24. Okay, this is way smaller than like 10 raised to 12, 13 times smaller than that. Okay, very small amount of electron hole pair is generated. Okay, at room temperature. Okay, okay. So now, so this is the picture for the intrinsic semiconductor. Okay. Now, what we can do, we can dope it. Okay. So we can dope it with two types of things. One is that a dopant where the valence electrons are one five, okay, because silicon has four. So something like arsenic, phosphorus, antimony. Okay. So what do you mean by doping? So doping meaning the density, okay, doping density again should be way lower, smaller than the density of silica. So you can treat it as small perturbation. Again, the silicon density is set 23, 24. The doping concentration if it is in the of the order of 10 raised to 15, 16, so way smaller than that. Meaning two dopant electrons don't interact. This is important. If they start interacting, then it is not doping, it is alloy. Okay, There is a difference. Okay, doping means small. So doping meaning you dope something, but it still doesn't change the band structure of a material. So we had silicon, the band structure will be silicon even after doping, but there will be some changes that we need to understand. This statement is very important. Okay, do you understand what I mean? So point number one, doping density is much smaller than the uh, host density. Host density. Okay, that means two dopant atoms are substantially far away. Okay, that they don't interact. That means then the host material's band structure will be unchanged. Okay. Okay, now, so we have this arsenic, okay, at room 0 Kelvin it is like a frozen. So, but this electron seems to be free, right? Kind of loosely bound. Can I say this electron is loosely bound? Okay, can I say? Okay, so if this say here, what we needed to do, like you need to break, provide enough thermal energy to break it, but it is very loosely bound, right? Because it is not participating to any bond. Okay, that means with a minimum of thermal energy this should be free. Do you agree or not? Okay, if this is free then it will become a free electron. Okay, that means how much energy is needed? What do you call that energy? Ionization energy. Okay, for hydrogen atom, suppose we have one electron, right? So you need to take that hydrogen atom from its core to infinity, right? But here, why do you need to take this electron? We have conduction band, valence band, right? Here you need to take this electron from here to infinity. So, sorry, not infinity, conduction band, right? That's all.
Sir, when if electron is removed, then any hole is not created.
Then the hole is not created. Okay. So now we can model it. So this is called ionization energy. Okay. So we can model it in different way. We can assume this is like a hydrogen atom sort of picture. We have this electron as if, okay, it is like a hydrogen atom, meaning it will be, okay, rotating around the nucleus of arsenic. Okay. But the background here in hydrogen atom, it is air, right? Vacuum, right? But here the background is silicon. What do I mean by that? I mean, so this is some sort of energy, right? Hydrogen, okay? This is the energy of electron of a hydrogen atom, okay? For hydrogen atom, the K is 1 for vacuum, okay? But here the electron is in the background of silicon. Okay, if it is in background of silicon, then we must use K is whatever dielectric constant or permittivity silicon has. Is this clear? So this loosely bound atom, sorry, this loosely bound electron is in the silicon and it is just rotating around. Okay, loosely bound. So that loosely bound, we connect that concept to hydrogen atom as if we have one electron in the hydrogen atom. But here that hydrogen atom is not in vacuum but in the silicon, the sea of silicon. Okay, that's all. So now if you put these values, then roughly, let me see if I, okay, this value will be like 30-40 milli electron. Okay, so you can briefly, so this is already 13.6, so square of that kind of 100. So m star by m star is the effective mass, right? And m naught is a free electron mass. So m star is way smaller than that, maybe 20-30% of that. Okay, so all together, okay, you can get it immediately, right? So already I can see 100 and there again another 100. So it should be in the millivolt range, you know, 30-40 millivolt. Okay, so note that the band gap, so for the silicon, sorry, for hydrogen atom, the ionization energy is minus 13.6. Okay, and here in electron volt, but here it is in millivolt. So very less energy is needed because it is loosely bound. Okay, that's why I'm using this phrase loosely bound. Okay, Yeah, and also you can find the radius. Okay, this radius is also from this you can calculate. I'm not deriving it. I'll derive that in my notes, or you will also find in Niemann's book. But I think that's not really essential. But anyway, from this you will get to have some idea. Okay, what is the typical radius? Okay, yeah. Okay, so now here, then how do you model it? So what is the equivalent diagram of this? So we should have same conduction and valence band, but we must have a donor energy level. Donor energy level comes from this energy level. Okay, we have used a dopant. Okay, so this has extra electron. Okay, but right now we have just figured out the ionization energy is very less, of the order of 20-30 milli electron volt, where the band gap is 1.1. That means the dopant energy level should be very close to conduction band. Do you agree? If it is very close to conduction band, then that means with little bit of energy, it can jump from here to there. That little bit energy is like 30, 40, 50 milli electron volt. So you can just put the values here, 11.7, and you can find that it is like 40, 45 milli electron volt. Okay? Is this clear? Does it make sense? Okay? Yeah. So now there are two processes. One is that, so you get free electrons. Okay, you get free electron because of the doping, because this electron is loosely bound. Okay, with some high, if you just slightly increase the temperature, we'll actually derive it. Okay, later on. But for the time being, just assume that if you just apply a little bit of thermal energy, then we can get this free electron. Okay, and in addition, we have this process still going on. Okay, but now, so these thermally generated electrons, okay, or electron hole pairs are less in number, Ni. That means now if doping density is higher, say 10 raised to 14, 15, that means the total number of electrons of this system will be the doping carrier concentration, roughly. We'll figure it out, we'll mathematically derive it, but roughly. Is this okay? Is this okay? Okay. So this material is called N-type semiconductor, and this is known as extrinsic semiconductor. N-type extrinsic semiconductor. Okay? Any questions? Okay. Any questions? No? Okay. Now instead of doping with arsenic or antimony or phosphorus, we can also dope with materials like boron, aluminium, where the valence is 3. Okay, that means we have a missing electron. So here the bond is not created. Okay, so that means we have a vacancy. Okay, or by default there is hole, because always electron from adjacent can hop. So that doesn't cost much energy, unlike this process, because here if we have n number of bonds at a given time, even this electron hops here, still you have a number of bonds at a given time. So this is not cost effective. So here in this case, we assume that the electron is orbiting around arsenic in silicon background. Here you can think a hole is orbiting around boron in silicon background, and eventually you can again define similar type of ionization energy for that. Okay, here ionization energy is the amount of energy needed to get an electron, okay, or accept an electron. Okay, what do I? Yeah, 23, 24. Hmm? Yeah, so what I mean is the following. So here also we have conduction band and valence band. Okay, but here, because of this boron doping, we will have a dopant energy level close to the valence band. Okay, the reason is it is so close to the valence band that it can accept electron from, as shown here. Okay, from one of these places. Okay, and it will be ionized. And when it is accepting electrons from here, then what we get? We get holes. So in previous case, so we had a loosely bound electron. Okay, so when it is donated, so the donor atoms become positively charged because it is losing electron. Okay, and we get free electron in the conduction band. Here is the other way around. Acceptor state, or this acceptor energy level is accepting electron. As it is accepting, it will be negatively charged, and therefore we will have holes in the valence band. Is this clear? Okay. So now, so this is the mechanism by which we can get excess holes. Okay. So this process is still there. This is thermally generated electron hole pairs. Okay. Yeah. So, but again, the dopant atom density, if it is higher than the Ni, then the whole concentration we can roughly write. Okay. This doping density. Okay, roughly. Is this clear? Okay. Okay, but this is an intuitive understanding. Okay. Okay, so here the bottom line is whenever we are doping, it means that the density is much smaller than the density of the host atom, and we are not changing the band structure of a material. And depending on the doping type, either it can be donor type or accepted type. In one case, we will have excess number of electrons. In another case, we will excess number of holes. That means by changing doping, we can tune the carrier type and carrier concentration. We are not quantifying it, we will quantify it soon. We are just trying to understand overall the broad picture. Is it fine? Okay? Okay. So, any questions? No? Okay. Then, as the next step, now we like to slowly connect this to the Fermi energy level and the density of states. Okay? And then still we'll be trying to have intuitive picture, and then we'll derive it. Okay. Yeah. So this is what density of states looks like. Okay. For conduction and valence band. Do you agree? We agree. Derived it, right? Okay. And this is what the Fermi function looks like at 0 Kelvin. Okay. And how do you define the carrier concentration? Integration over this and that. Sorry, integration over energy, density of times this probability function. So for this case, at 0 Kelvin, see, this is the Fermi energy level. Okay, above Fermi energy level, we cannot have any electrons. So that means electron concentration should be 0, right? So this is just mathematical way of understanding. Previously, that was intuitive. Is it okay? But yeah, they're the same picture. But as we increase the temperature, then what happens? So previous it was completely intuitive. Now we are trying to see the connection between that and this density of states and Fermi Dirac stat. Okay. As you increase the temperature, what happens? Density of change states don't change much, but this smears out, right? Okay. So this becomes like this. Do you agree? That we have seen in the last class. Yeah, so that means tail of the sum, there is some probability, as he was saying. Okay, there is some probability here, and this is 1 minus f. Why I'm plotting 1 minus f for holes. Okay, we are interested in electron and holes. Okay, so now you need to find the carrier concentration. So you need to multiply that for this energy, this to that. Okay, right? So if you do it, then you will get, say, the carrier density profile like this. Do you agree or not? Say carrier density should vanish at very high energy. The reason is F is 0. Do you agree? Here it is 0. The carrier concentration should be 0 here. And somewhere that means in between it should peak, right? So total area of this. So the total area is F, then D, this integration, right? This is the area of that. Total area of this is the number of electrons. Is it clear? simple integration. Just I'm trying to show with schematics, trying to explain integration with schematics. Okay. Okay. This is this area, and this is the area for the holes. Electron and hole, if they are same number, so this area should be same, right? They are same in number. Electron holes are always in pairs. Okay. Okay. That's all. This is what we have for the intrinsic. Okay. Now what will happen for the extrinsic? Let's focus on the n-type material. Okay. So for n-type material, what you know so far, we must have more electrons, right? Right? You agree? If you need to have more electrons in system, what type of modification will you do here? What is the thing that can be changed? Will you change density of states? Density of states? No, right? Because it is a property of silicon. It is there, whatever. Then only parameters are Fermi energy level and nothing else, right? You cannot change the Fermi-Dirac stat. That expression you cannot change. Only the thing that you have in your hand, EF. Okay? Then EF should be raised or it should be lowered. If you want to have more N. If you want to have more N, that means you want to increase this overlap. If you want to increase this overlap, meaning you have to bring this entire thing towards the conduction band, right? If you bring it towards the conduction, so now it is symmetric. Whatever overlap you have it here, you also have same overlap. That's why it is giving you the same result. If you want to have more overlap here, it should be raised, right? So something like this, but this is at 0 Kelvin. So even at 0 Kelvin, nothing happens because it is sharp, okay? Because EF is still in the band gap, right? But as you increase the temperature, now see you have more overlap here, and here the overlap is less. Is this evident? If the overlap is more, then the integrated area will be more. If it is more, that means it will be less by default. Okay? So if it is more, that means if it is less, that means something should be constant, right? That is the product of these two areas. Okay? So n times p, we will derive it, but just a teaser, okay? N times p will be constant. Is it clear? Okay? Any questions? Okay, so this already we have explained. I'm not spending time. So this means this mechanism, okay? Okay, what is the other way around? For the p-type material, what do we expect? We need more holes, right? If we need more holes, meaning now we need to increase this overlap, right? So we'll shift this Fermi energy level towards the valence band. Okay, something like this. But again at 0 Kelvin, so here there is no electrons, okay, everything is occupied. But as you change the temperature, it will be smeared out, okay, again same story. Now here overlap is small, much smaller than that, okay. So the integrated area will be smaller and it will be large, okay. So this is consistent what we have discussed previously. Is this clear? So then what do you learn from this slide? I mean, what is the summary? So always whenever we are teaching, you should think it in this way, broad perspective and detailed. Okay. So what is a broad takeaway message? Broad takeaway message is that if you want to have more electrons in system, in a semiconductor, your Fermi energy level should move towards the conduction band. Or if you have more holes in the system, the Fermi energy level should be closer to the valence band. Okay. So in the previous class, we have discussed the importance of Fermi energy level. So this is also another implication of that. Okay. So far looks fine, but still it is like intuitive, right? It is understandable. I hope you are getting, right? At least the overlap is more, okay? But now what you need to do? Quantify it, right? You are electrical engineer. You need to exactly know. You need to find out what is the current, okay, what are the carrier concentration. Then what you have to do? You need to find this integral, that's all. Okay? Ready for that? Okay? Okay, that is done here, okay? So in a real system, we can have very complex density of states, but near the, as I keep mentioning, near the conduction and valence band, we can always have density of states like that. Okay, yeah. Now, so this is the Fermi energy level. We need to essentially do this integration. Now, if we are interested in finding number of electrons, okay, so we need to start from the conduction band minimum. Say this is EC all the way to vacuum. Okay, so here we are assuming that okay, this is like going okay all the way to vacuum. But anyway, it doesn't matter. The reason is that Fermi function anyway is 0, okay, for higher values. So it will not blow up, okay. Fine. So whatever density of states we derived, we have written it, and whatever Fermi data stat we have, I have just written it. Simple. Now we need to just solve this integration, right? Okay. That's not that big. I mean, it's not that big deal. How to do it? So one thing is that in a homework problem, I'll ask you to solve it numerically. Okay. And you will compare that numerical result with the approximation we will consider now. Okay. So one of the approximation is, let's get rid of this 1. Okay. If we have only exponent, your life would be much better. Okay. And that is possible when the semiconductor is non-degenerate. Okay, we'll just see that soon. Okay, and another thing we can do, so I can write this E minus EF in this form: E minus EC plus EC minus EF. Okay. Okay. So then E minus EC I can consider as a constant, and then okay, what I mean is the following. So first thing is that this Fermi deduct stat, I just get rid of this 1, okay, and I'll just use it, and this is possible if E minus EF is more than 3 times of, I mean 3 kT. This is called non-degenerate. Okay, you will appreciate this only when you compare this approximated result with the real simulated data. Okay, so you just need to simulate it numerically. Homework problem will be given for that. Okay. Okay. So then, yeah, we just consider E minus EC is eta, some constant. Okay, this is how you solve, right? How you do integration, right? Okay, then I don't need to explain it. So there will be different constants will come outside of the integral. Whatever constants are there, and whatever important things we have, those will be inside this integral. Fine. So now this integral is a special form. Okay. So this is a very well-known integral, and in physics or engineering, this kind of integral will keep coming. Okay. So in physics, always it is there. In engineering, you have come across such integrals several times. Yes, this is called gamma function, beta function, integral of Gaussians. Okay. These are the things you will always come across, even in signal systems. Okay. So this is the result. Okay, if you have seen this integral, so its result is already known. Okay, so using these values, we can actually find okay the approximated value of n. Okay, so this n will be like nc times this, where nc is, as you can see. Okay. So what you need to understand is that to find NC, this is important. You need to do this integration. That's all. Okay. So we have this Fermi function, Fermi coming from Fermi deduct stat, and the density of states, which are already derived. And after that, it is an integration. Okay. So conceptually, should not be complicated thing. Okay. And now you are doing like simulations, okay? So a lot of simulation problem will be given and we are giving. So you should solve it numerically and test it, okay? Okay. So what are the things to note here? So this constant term, whatever you have, has Mn, effective mass, okay? And it also has temperature. That is important to note, okay? Okay. Second thing is that, so this N is proportional to exponent of EC minus EF, and there is a minus sign here. So we can call it EF minus EC, okay? So what does it mean? If EC is close to EF, we will have more electrons. Do you agree or not? So consistent, whatever we discussed earlier. Consistent? Do you agree or not? Very simple, right? No, you have to say. If you don't say, I don't get. So if EF, the Fermi energy level close to conduction band, okay, from this expression, do you get more number of electrons or not? Yes? Okay. So things are consistent. Okay. So I can ask you another question, how to find Mn here. This is the effective mass, right? So in EK diagram, you also had effective mass. But here the effective mass is different. The definition is different. Okay. So I'll explain again what is the relation between the effective mass that you derive from the EK diagram and here. Okay. I think, yeah, so I'll explain it again. But already homework problem is given. That's why you should solve homework problems for that. Okay. Yeah. So same thing we can do for holes. Fine. We can do the same thing for holes. So what are the things we'll do for holes? Integration limit should be, yeah, EV to minus infinity. And here the Fermi function should be 1 minus Fe. Okay. So we'll not do it. I just write down the final expression. So expression will look similar. Okay. See, these are identical. The important thing that you need to remember here, there is a T dependence. NC, NV, they depend on T. So it is T raised to 3 to the power 2. Okay. That's what it is. Okay. And here, is this consistent with what we discussed? If the Fermi energy level closer to valence band, do you get higher number of holes? Do you get? Yes, no? Yes? Okay. Okay, so far things are consistent. Okay, now for the okay, so now you can do different things. So let's consider, so this is quite general expression, okay? So that means as you change the doping, so this EF will change, right? As you change the doping, EF will change. Now if you consider intrinsic semiconductor, what do you get? N equals to P or N naught, then I write it N naught and P naught, okay? N naught equals to P naught and I call it Ni. So if you put N naught P naught here, and for intrinsic material, Fermi energy level lies nearly, we'll derive it soon at the mid gap. Okay, so from that you can get the intrinsic carrier concentration. For example, suppose so band gap is 1.1, right? Suppose EC minus EF is 0.55. Okay, and other values you can actually find. So 2 pi h bar k at room temperature, T is known, M is known. Okay, if you put all the values, you will find NC. Okay, So if you put all the values, the roughly the number you get is Ni. Ni meaning 1.5 10 raised to 10 per centimeter cube for silicon. Okay. So question can be asked, like silicon has a band gap of 1.1. If I have the carrier intrinsic carrier concentration 10 raised to 10, if I reduce the barrier, okay, then whether you will get more carrier intrinsic carrier concentration or less. Tell me. More? Why? Yes. Okay. So mathematically you should understand, and intuitively you should appreciate the same thing. So here just I have taken this product in okay product of these two. If I take product of these two, what you get? NCNV and exponential Eg minus KT. Okay. As you decrease the Eg, your Ni increases. That's why germanium has higher intrinsic carrier concentration than silicon. Gallium arsenide will have lower intrinsic carrier concentration than silicon. Clear? What about the temperature? If I increase the temperature, intrinsic carrier concentration will increase or decrease? Will increase because of this T cube dependence. Okay. How do you physically understand? This intrinsic carrier concentration is essentially the number of carriers, okay, which are able to excite from the valence band to conduction band. If the gap is small, there will be more number of carriers, right? Make sense? That's why you have this dependence. Now, as you increase the temperature, there will be more carriers as well. So that's why it's also proportional to that. Okay? These are the things one can ask questions based on that. Okay, so if I have temperature, intrinsic carrier concentration at a given temperature, what it will be at other temperature, band gap, materials, okay? There can be different permutation combinations you can think about. Okay? Okay. So now, so this was for the intrinsic, okay? Yeah, so at intrinsic, so here let's define somewhere we have the Fermi energy level almost at the mid gap. Okay, I define it, I just call EI equals to EF. Okay, for n-type materials, so now Fermi energy level is close to the conduction band and p-type close to the valence band. Okay, so for n-type material, I can write, I'm just writing same expression here. You see, instead of EI, I'm writing EFN, just N for n-type material. Is it okay? So now what I'm doing, I'm just writing EC minus EI and EI. Okay, can I? Okay, fine. Okay, if this is the case, then so I can take this guy. So have you seen this thing before? Here, this is N naught. So this NC times exponent EC minus, there is a minus, EC minus EI by KT. So this entire term is N naught. Okay, so then I can write N naught meaning Ni, then I can write N equals to Ni exponent EFN minus EI by KT. Okay, simple algebra. Again, this makes sense, right? So now, so what this equation is saying, like if you know the intrinsic carrier concentration, okay, then what would be the electron carrier concentration after doping? If you know how much Fermi energy level you have shifted, then you will know like how much how much carrier concentration you have, or vice versa. If you know this is the carrier concentration, then effectively you should be able to say where is the new Fermi energy level. Okay, so we can do the same thing for holes. So for holes, so it should be EI minus EF. Okay. Okay. Fine. Any questions? Okay. So one thing is that NP is Ni squared. That is always true. Okay. So you can just take a product of this N and P. Okay, if you take product of this N and P, you can just do it yourself, then you will find that it is always constant. Also we have seen, so that was the essence, like I keep mentioning that the integral, there were the integrals. So if you change the Fermi energy level, so one will grow, another will shrink, but total meaning product of them should remain constant. Okay, that is the mass action law. Okay, so we have changed the Fermi energy level, so that means we are changing electron and hole concentration, but we are changing it such that, okay, that the product of N and P will remain Ni square. Just put N and P, you immediately get it. Okay, Ni square. Okay, another important consequence is that we need to exactly know where is the Fermi energy level of this intrinsic semiconductor. Okay, so I already mentioned, but here we are just trying to quantify it. For intrinsic semiconductor, N equals to P equals to Ni. So this is N, expression of N, this is expression of P. Do you agree? Fine. This expression of N, this expression of P. I can take log both the sides. If you take log both the sides, and after a simple calculation or modification, you will get this expression. Okay, so why do you have this M, from where are you getting MP star and MN star? Because within NC and NV you have this MP star and MN star, right? So it actually tells you that this EI is not at the mid gap. It will be at the mid gap if MP and MN, if the effective mass is same, then it will be at the mid gap. But if they are slightly off, then then the EI will not be at the mid gap. It can be slightly shifted.
Even for intrinsic semiconductor.
Yes, yes. This is for the intrinsic semiconductor. EI is for the intrinsic semiconductor.
For intrinsic semiconductor, EI is at mid gap or
EI is not at mid gap. It is shifted. It is slightly shifted because of this MP and N, because of NP and NN. MP and MN. Okay. 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 So now let's move on and let's see what we have. Okay, so now we need to write the charge neutrality equation. Okay, so here every time we dope, okay, every time we dope, we ask this question, what is the total charge inside the system? I'm saying total charge. No matter whether you dope or you don't dope, the system is neutral, right? Overall system is neutral, right? This is also one interview question generally asked. Like if I dope a material with arsenic, it becomes N-type. So what is the charge of a system? Okay, if students say that it is negative, then it is already gone. Okay, the system is neutral. Okay, the reason is the silicon is neutral. What are you doping with? What are you doping with? Arsenic. There's a neutral atom. So if you are doping with another neutral atom to a neutral atom, sorry, to a neutral system, the whole system should be neutral. That's why charge neutrality is important. And if you solve charge neutrality, then exactly you will know the carrier concentration. Okay. So now let's do a bit in more generalized way. Let's assume that we are doping with Na and Nd. We are doping with Na and Nd. Okay, and when we are doping with Na and Nd, let's assume that we have electron and hole. P number of electron and N number of hole is present in the system. Fine. We now need to understand this N and P relation. Okay. Okay. So what is the net charge from the holes? E times P. Total number times E is like 1.6 10 raised to minus 19 coulomb. And for electron minus En, because electron is negative. And this is the donor atom. Okay, donor atom becomes positive. right? It donates and it becomes positive. So if I have Nd number of donor atoms, so E times Nd, and acceptor atoms become negative. So there is a typo here. Trying to, so this is, oops. Okay, I hope you understand, right? What I mean. Minus, yeah. Okay, right? Okay, so this is one equation that we have, and always mass action law is held. There are two equations, and we need to solve them to find N and P. We have two unknowns, the N and P, right? So that N and P will be in terms of this Nd plus and Na minus. That's all, right? Two equations, we can solve it, right? You can try to solve, but I'm just giving you the final solution. So if you put all this, so you will get this kind of quadratic equation, and if you solve it, then you will find that. Okay. So if you know N, then how do you get P from this Np equals to Ni square? Is it okay? Yeah. So previously I said that if okay, now take some cases. Okay, suppose Nd is 10 raised to 15, Na is 10 raised to 12, Ni is 10 raised to 10. What would be N? Sorry, 10 raised to? I'm giving you Nd is 10 raised to 15. Let me just write. Nd 10 raised to 15. Na 10 raised to 12, all per centimeter square. And Ni 10 raised to 10. Okay. So what would be the electron and hole concentration for this system? Put all the values. So this Nd minus Na square, okay, this is very large, right? So Nd is 10 raised to 15, Na is 10 raised to 12. So forget about 10 raised to 12. 10 raised to 15. So this 10 raised to 15 is way larger than the Ni square. Okay, then forget this Ni square. Okay, so here you have 10 raised to 15 by 2. Here you have 10 raised to 15 by 2. So altogether 10, approximately 10 raised to 15, right? That what we intuitively understood before. So that means what I try to uh, tell you that this equation, whether it makes sense or not. Makes sense? Okay? Okay. Any questions? Yeah, correct.
So when we are dealing with real silicon, let's say so basically, if you look at the net carrier concentration, then we backtrack and find the Fermi levels like from the expression.
So actually, it works in both ways. Okay. You can backtrack it and find the Fermi energy level, or yeah, sometimes the concept of Fermi energy level actually helps you to understand things. For example, if we have two different materials having two different carrier concentration, then and if you combine them, what will be the uh, net new configuration? Okay, in that type of cases, Fermi energy level is very essential. The reason is that then you can think or assume it like water level. We have water tanks. If you connect them, then the water level is aligned. So you need that starting point. So once you have the starting point, once you have that Fermi energy level aligned, then from that you can build on other things. Okay, like where the other conduction and valence and energy levels will get into that in the yeah. So and from there on you will see like band bending. When you have band bending, then you essentially have electric field. So essentially the whole electrostat is there, but you need the starting point. That starting point will definitely farm energy level will help you.
It's good for like understanding.
It is good for understanding farm energy level, yes. But in general, yes, if a material is given, okay, so once doping concentration things are given, so if you know the carrier concentration, you can tell that, hey, here if I should have the farming energy level. Okay. Okay. So now the last part, okay, which is very important. So here we have Na plus. This is very annoying. So Nd plus and Na minus. Okay, so I will correct it. Okay, while I. Okay, let me still. So this should be Na minus, right? Nd plus and Na minus. Okay. Okay. So what is this Nd plus and Na minus? Okay, and how? So this is the expression. Okay. So, but uh, is it valid for the all temperature range? That's the question. Then you need to also understand how you had that electron and holes. So again, okay, let's recap. So what we said is that when you dope, okay, depending on the doping, whether it is N-type or P-type, we get donor or acceptor energy levels. Okay, those energy levels are close to conduction and valence band. So donors donate. Okay, if donors fully donate, if we have Nd number of donors, if Nd number of donors fully donate, then we get Nd plus ions. Okay, same number of ions, and we get same number of electrons, right? But that is temperature activated process. Okay, if we are very low temperature, at very low temperature, so it will not be able to donate something like this. Say at 0 Kelvin. So here, whatever electrons we have in the donor state or acceptor, okay, here this is just example for donor, it is just frozen there. It doesn't have enough energy. But when you slowly increase the temperature, then this starts ionizing. And if it is fully ionized, then you can say this Nd plus is Nd. Is this clear or not? At low temperature, you don't have all the donor atoms are ionized. That's all. Okay. So then, okay. So then what happens? So if I want to suppose, okay, my question is, suppose I am doping an intrinsic silicon with 10 raised to 15. Okay. And if I ask you to find number of electron and hole carriers as a function of temperature, how would that look like? That's the question. The answer you already know, right? You will immediately say 10 raised to 15, right? But 10 raised to 15 for all temperature. So 10 raised to 15 is the answer, assuming all donors have donated, meaning it is fully ionized. So there is a regime, okay, when that is valid. We call it extrinsic. Meaning in that temperature regime, it is extrinsic. Because when temperature is lower than that, then dopants are not activated. They have not donated all electrons. Then again electron concentration will decrease. Is it clear or not? Okay? Okay. But what happens, so this is called freeze out. And what happens very high temperature? So very high temperature, so there are two processes. One is that, so we have this dopant, so here donor, so we are getting electrons from donor, so we cannot have more than Nd number of electrons. But in addition, thermal electron hole pair generation is taking place. That is always a continuous process. Okay, at very high temperature, this will dominate. And this is exponential in temperature. Why? We have decided, seen, okay, if you look at the carrier concentration expression, Okay, it is like in Ni square is proportional to T cube e raised to minus Eg by Kt. Okay, so you have T cube dependence and exponential dependence. So that means at a very high temperature, okay, so suppose Ni, so at room temperature for silicon, say Ni is 10 raised to 10 and our doping is 10 raised to 15. Okay, so I said that at room temperature 10 raised to 15 is the electron concentration for this case. Okay, now if I increase the temperature to 600, what will be the intrinsic carrier concentration that time? You can calculate. Okay, suppose that time the intrinsic carrier concentration is 10 raised to 18. That means what would be the electron concentration? Dopant concentration is smaller than that. Electron concentration will be 10 raised to 18, right? So this is like exponential growth. So slowly, the electron concentration will match to this limit. Okay, so this is called extrinsic. This is called extrinsic uh, limit. Okay, so there are three regimes: intrinsic. Sorry, so this is intrinsic because you have doped it, but the material is not behaving like extrinsic material. It is behaving like intrinsic material at very high temperature. So this is the intrinsic temperature region. This is extrinsic temperature region, and this is the freeze out region. Okay, this is very important. There will be questions on that. I'm telling you. Okay, in quiz and midsem. Okay, I think this is whatever I was discussing, I have already written. Uh, yeah, so here I will give a homework problem where you can actually, okay, so this is, I will not derive it, although Robert Peters's book has some derivation. Now the question is, uh, what is this ratio? So Nd plus and Nd. First tell me what is the maximum value we can have Nd plus by Nd? 1, meaning all ionized, right? At very low temperature, it will 0, right? It's not ionized at all. Okay, so generally it goes like that. Okay, it takes this expression 1 by 1 plus something. This something is always non-zero, I mean greater than 0. So this term can be 1 or less. Okay, okay, yeah. So, yeah, question?
NCA and MBA font. There, how are we getting KT for 3 by 2?
Yes, so that is the limit. Okay, that is not evident here in today's class. So if you, what I said, if you integrate that numerically, okay, or without that approximation, it will follow some track, and with this approximation, whatever we have, uh, so you will see the deviation, prominent deviation, when the energy difference is less than kT, or sorry, less than 3 kT. Uh, okay, I'll answer to your question. Okay, just give me 2 minutes. Any other questions here on this? Any other questions? Okay, so here note that EF minus ED by KT is there. Okay, and here for Na it is EA minus EF by KT. There are constants, or these are called degeneracy factors. We'll not get into that. So the question I will give for the homework problem. Last time that question came in the quiz and probably in the midsem as well. Uh, I'll give you like temperature for silicon 10 Kelvin, 20, 30, 40, 50. You can try to find the ionization, okay, percentage. But how will you do it? What is the value of EF you will consider? ED is fine. The dopant concentration is, dopant energy state can be given, okay? But how do you find EF for that case? Okay, so that you have to do self-consistently. Okay, Self-consistently meaning, I'm telling this that you have to do it, okay? So you assume some value EF, okay? Say close to ED. If you assume that value of EF, then you get some number, and you put that number into charge neutrality and see if it is consistent or not. If it is not consistent, then repeat this process. Repeat this process such that it is self-consistent with the charge neutrality and the carrier concentration you have from here. Okay, so self-consistently you need to solve it and then you will be able to find it. Okay, I'll give you, so the thing is that it's not that easy to explain now. If you solve it, then you will understand. Okay, so you need to solve for the problem. And another important thing, see, we assume that the dopant concentration is very low here. If dopant concentration is low, then only this equation work. I'll also give you one question, like here, if you consider the dopant concentration 10 to 18, it will just break down. Okay, that also you should do. The reason is, if dopant concentration is high, then instead of having one dopant layer, energy level, we can have a distribution. We cannot use a simple formula. The simple formula roughly works when the doping concentration is quite less, okay, of the order of 10 to 13, 14, 15. Okay, yeah, I'll answer to your question. Let me see what else do I have. Are there any questions here? Oh, okay, so can you tell me one thing? Suppose we have this n-type material doping 10 to 15. So at extrinsic limit, Fermi energy level is close to conduction band, right? I can give you numbers and then you can calculate. Suppose this is like 0.7, okay, electron volt, I mean electron volt, stuff like that at room temperature. But what would be the gap? This EC minus EF at 500 Kelvin. Without solving, I'm asking because you should be able to answer this without solving, just from this graph. Huh?
EC minus EF,
Huh.
half of the.
Okay, that's the right answer. Okay. The thing is, so at elevated temperature, what's happening? It is like intrinsic. In intrinsic, why do you have the Fermi energy level? Near mid gap, right? That's why I don't know if I have that figure or not. That's why in the book you will find that the Fermi energy level as a function of temperature. Okay, that you should figure out from the textbooks. That I don't have. Anyway, we don't have time for generation recombination.